In the last few months, three letters forever changed the course of AI: GPT. Buzzwords like ChatGPT and GPT-4 became common knowledge. But in the last couple of weeks, one more buzzword has been added to this mix and has been gaining more and more attention, which is llama. No, not this llama, this llama. And there's a pretty interesting story behind it. So, what is it? I'm going to do a deep dive on the background and what makes llama so special. Latest developments such as giving GPT access to plugins like Stable Diffusion and Search has shown that the sky is the limit. With the breakthroughs OpenAI had with ChatGPT, that is, it being remarkably aligned with user requests than a pre-trained LLM, OpenAI leaned towards more and more secrecy. If successful, the market it can hold a monopoly over and disrupt is not small. OpenAI resorted to keeping the datasets, model architectures, training mechanisms a little too close to the chest as it made more and more progress. Naturally, this intensifies researchers and companies to wonder what makes these models so special and try to replicate and even surpass. We know that the instruction-based fine-tuning method proposed in InstructGPT is the main enabler for ChatGPT. But it's not that simple either. Other models such as Google Bard and Bing Chat did not get to a great start. These new-to-the-market models have gone through some embarrassing mishaps to be iterated on and become better. So OpenAI still seems to have the upper hand in this game, with some incredible capabilities demoed for GPT-4. This is when Meta AI said, "Fine, keep your secrets." This sets up the stage nicely for Llama. Llama was first announced by Meta AI as an attempt to democratize large language models or foundational models. This is not the first attempt Meta stood up to OpenAI. It also released OPT 175B, which stands for Open Pre-trained Transformers, in 2022, which is the open source alternative for GPT-3, which is, again, closed source. With Llama, in a blog post, Meta said that it will be slowly rolling out the package on a case-by-case basis to research communities and other industrial laboratories under non-commercial licensing. But few days after it announced this, the model mysteriously leaked on 4chan as a downloadable torrent link. This led to a surge of third parties hosting the model on GitHub and Hugging Face. Meta has filed takedown requests, but given how fast things spread on the internet, it is a little bit too late. On a different note, probably through official channels, researchers from all around the globe started releasing instruction fine-tuned models based on Llama, such as Stanford's Alpaca, UC Berkeley's Vicuña, and Databricks' Dolly. This may have fast-tracked and popularized the production of these fine-tuned models due to the leak. Although they're not yet on par with ChatGPT, they're definitely getting better. For example, Vicuña 13 billion has performed on par with ChatGPT, up to 90% as evaluated by GPT-4. Vicuña and Dolly weights are released and can be accessed by anyone. Stanford's Alpaca was released as an interactive website, but was taken down quickly due to hallucinations and misinformation. Since the basis of this newfound open source AI revolution was Llama, let's go through the motivation for Llama and see what makes it tick. Problem with GPT-3, which forms the base for ChatGPT, is its inaccessibility. It's massive and cannot be fit on a single GPU. Even if you had the compute resources, some datasets that GPT-3 uses to train are not publicly available or documented, such as Books 1 and Books 2. And GPT-3 weights are not available for public download either. To get some perspective, GPT-3, which has 175 billion parameters, cannot be fit on a single GPU. Wikipedia says it takes about 800 gigabytes to just fit the parameters of GPT-3. To recap, LLMs are inaccessible because of their computational requirement and the secrecy about their datasets. Now let's understand the motivation behind Llama. Llama is developed by training a smaller model on more tokens, specifically a 70 billion parameter model on 1.4 trillion tokens. It is trained only on publicly available datasets, unlike GPT-3, but it performs better than some other models trained on publicly available datasets only, such as GPT-NEO-X or Bloom. Let's learn about the size and the size of the dataset. Where did these 70 billion and 1.4 trillion magic numbers come from? I have to bring your attention to a different paper by DeepMind called Training Compute Optimal Large Language Models. Here, they show that current LLMs are oversized and should be trained on more sequences than they are currently. For example, GPT-3, which is a 175 billion parameter model, is only trained on 300 billion tokens. But to reach optimality, it needs to be trained on 3.7 trillion tokens. To give you some perspective, the current dataset of GPT-3 is 12 times smaller. Okay, how do we find the optimal model size and the dataset size? The idea is to fix a computational budget using flops and find the optimal number of parameters and tokens that it satisfies. Increasing either increases the number of flops required. But if you increase the dataset size, you can still have a smaller memory footprint and a lower latency model. So, how do they do this? They actually use 3 different methods and show the results are the same. In one, they train a variety of models ranging from 70 million parameters to 10 billion parameters on varying lengths of training sequences and obtain the training loss. Then they get the envelope of lowest losses to collect some data points about the number of parameters and the dataset size. Then they fit 2 regression lines, one for the number of flops and the number of parameters, the other one for the number of flops versus the number of tokens. With that, they can extrapolate how many parameters and tokens satisfy a given fixed flops budget. In this paper, they show that as the compute budget increases, the model size and the amount of training data should increase approximately in equal proportions. They use a different model called Grover as their baseline, which is a 280 billion parameter model. They show that if you train a 70 billion parameter model on 1.4 trillion tokens, you get the same number of flops as Grover, but performs better than Grover in most cases. In other words, to gain the optimal model, you need 20 tokens per parameter. The outcome here is a fresh new LLM called Chinchilla. Alright, now back to Llama. In terms of the model architecture, it's a transformer model. You can see the details in the table in their paper. Some notable architecture details are they use pre-normalization, which is borrowed from GPT-3 paper. Layer normalizations here are applied at inputs for each sublayer, which is the self-attention sublayer and the feed-forward sublayer. This is different from how it's done in the original transformer model, which is to apply the layer normalization at the output. They use a different nonlinear activation called SWIGLU, and finally, they use rotary positional embeddings, or ROP for short. Let's go into a bit of details about how ROP works. ROP is a pretty clever idea and has introduced a method to incorporate the positional embeddings into a transformer. Before ROP, there were 2 alternatives: absolute embeddings, which you train jointly with the model, or the relative sinusoidal embeddings. The idea behind ROP is pretty simple. When computing the attention scores between a query, QM, and a key, n, 3 things should matter: the mth input, which is xm, the nth input, which is xn, and then m minus n. In other words, the relative distance between two birds. If we rotate qm and kn by some degree that is relative to their absolute position, the angle between them gives the relative difference. Let's look at some maths. Specifically, we compute qm, kn, and vn to compute the attention scores. This is similar to a normal transformer, but we're not using the positional encodings just yet. Positional encodings come into the attention computation, and that is computed as shown here. Here, R is a rotation matrix, which rotates a given matrix by some theta when multiplied by. When you multiply Q by the rotation matrix, Q is rotated by an angle proportional to M. When you multiply Kn with the rotation matrix, the same thing happens, but with an angle proportional to N. Another way to understand is if you assume WQ equals WK, and let's say XM and XN correspond to the same token. If you have this equality, then QM equals Kn. Then you still have the attention scores being different because the relative positions are different for these two, though the inputs are the same. This is the main idea behind ROPE. I have linked the paper if you're interested in reading. Now let's talk a bit more about Llama. In terms of training Llama, it was trained on 2048 A100 GPUs over 21 days. This is not a small feat, if you ask me. However, when it comes to inference, the 13 billion variant of Llama can run on a single V100 GPU during inference. There are also reports on quantized version of the 7 billion Llama version running on a 4 GB Raspberry Pi and even a Pixel 6 phone. In terms of evaluation, they rigorously evaluate Llama on many different NLP problems such as common sense reasoning, closed book question answering, mathematical reasoning, code generation, etc. On most of these tasks, Llama comes on top of other large language models like GPT-3. These tasks are still a bit off from how you evaluate these models or how you interact with these models. But it's still interesting that Llama comes head-to-head with some of the larger models on language understanding. They also do a brief experiment on instruction fine-tuning Llama. This produces a new model called Llama-I. This new model outperforms other publicly available instruction fine-tuned models like FLAN-PaLM. FLAN-PaLM has a similar number of parameters to Llama. In conclusion, Llama is a transformer-based model that is much smaller than GPT-3, but is performing well in most areas. It comes in different flavors, smallest having 7 billion parameters and the largest having 65 billion parameters. The scaling laws applied to Llama comes from a DeepMind paper, which shows LLMs are not trained for longer as they should. Roughly, there should be about 20 tokens per parameter. Many models such as Alpaca, Vicuña, and Dolly were released as instruction fine-tuned versions of Llama and has shown promising results, taking big strides to a ChatGPT. The future is sure exciting. With GPT-4 rolling out and the research community looking into alternatives such as Alpaca, Vicuña, and Dolly, this space will only get more impressive. Hopefully, the future would hold less secrets about how these models work. If you're interested in learning about these kind of new cool technologies and developments, make sure you subscribe to my channel, Deep Learning Hero. I will see you soon with a new video.